Well, thanks for coming, at least for the first half, everyone. We'll see if I thank you at the end of the second half. So the focus of the talk today is on the Jeffrey-Bolker decision framework. We say framework instead of theory because these two things are often kind of conflated. And we really want to highlight the kind of background aspects of the framework and not the kind of normative decision theory that you can write down in the framework. So things like evidential decision theory, causal decision theory, that's the latter. That's the thing that we're going to talk a little bit about at the end, but mainly we'll focus on the kind of background space in which you can compare these different decision theories. So that's why we call it decision framework. Gerard will start off by talking about some things. We'll encourage you to interrupt along the way, kind of a little informal. We'll also feel free to punt it to Q&A or to our session after, in case we think it'll take us too far afield. There are some kind of optional sections at the end where we try to give some more upshots of the framework. And depending on how long the questions go, how much we get kind of into the details, we again may push those to the discussion after. Yeah, so feel free to interrupt us, and I'll hand it over to Gerard.
Cool. So like Daniel said, the main goal is to talk about Jeffrey-Bolker, their framework, but it's helpful to contrast it with the sort of background theory that's sort of the dominant approach, or dominant framework for thinking about rational choice within economics, and was already pretty much by the time Jeffrey was working. So that's the Savage framework, and then probably a number of people are somewhat familiar with Savage's decision theory. So we won't take too long on it, but just sort of go over it, the basics of the framework, and then with a main focus on highlighting some of its perceived limitations on the part of a lot of philosophers, which has sort of motivated the popularity of the Jeffrey-Bolker framework within philosophy. Okay, so what's the game Savage is playing, right? It's a very simple framework. So I have most of this on the handout. I put all like the axioms and theorem from Savage. We won't go through all the axioms or anything, but the basic framework starts out with two primitive sets. We have a set S of states of the world, and we have a set C of consequences. Okay? States of the world, these are things that are outside of the control. They're determined together with whatever act you take, what sort of consequence you'll get. And consequences, these are different things you might want to have. And so I'll draw a couple little sample decision problems. But acts for Savage, right, the things that are going to get expected utilities attached to them, A. These are really functions from the set of states to the set of consequences. So they're defined in terms of states and consequences. And then Savage assumes we have a primitive preference relation that's defined on the set of acts A. So agents express preferences over these different functions from states to consequences. And then the name of the game is to try to take this and place conditions on preference such that we're able to interpret the agent's preferences over acts as maximizing expected utility. So we want to move somehow from this to probability function and utility function pair such that the value of any act, right, the utilities are attached to consequences, the probabilities are spread over the algebra generated by the states, and we want the value of any act, or maybe we want one act A to be referred to another act B, just in case its expected utility relative to the measure P is greater than B's expected utility relative to the measure P. Right? So that's the goal. That's the name of the game. Yeah.
Sorry, what is P
yes.
and U?
Yeah, so P, right, we start with an agent who has preferences over all these different kinds of acts. We're trying to figure out from that, you could think intuitively, right, P is a measure of the agent's beliefs and U is a measure of the agent's desires, so it's probabilities and utilities, right? But we're trying to infer them from the agent's preferences. So P is going to be defined over states. States are the things that get probabilities attached to them.
So P is an element of the distribution of states.
P is a probability measure that's defined on the algebra that we generate from the states. So we have some set of states, and then different sets of states are propositions or events, if you want to call them, and they each get a probability attached to them by P. Right? For Savage, P is a finitely additive probability measure, though there are versions that try to get to be countably additive. Was that responsive? of what P is. So it's supposed to be a measure of the agent's, I mean, intuitively you can think of it as a measure of the agent's beliefs, right? It's something we're trying to construct. It doesn't show up anywhere in the primitives we're starting out with, right? We're trying to show that if these have the right structure to them, in particular if the preference relation is going to satisfy the right axioms, then we'll be able to come up with a probability measure and a utility function. Right?
Yeah,
Is this?
I think so, yeah.
Is it?
So
Yes,
we think of all uncertainty as living in uncertainty about which state we're in, rather than having any uncertainty about which consequences might arise from which act.
That's right, exactly. Yeah, all the uncertainty is about states, and all the utility, all the value is about consequences. Yeah. So this will be a difference with the Jeffrey frame. Okay, so the axiom probably to motivate some of the limitations of the. So I mean, it's and now you can see why it's like attractive to economists to start with just these simple sets and then a binary relation on the functions you can form from one set to the other, and you put some kind of simple, I mean, there's 7 axioms that are put in total. The first 6 are the only you need as long as the outcome set is finite. The 7th one is just for if the outcome set is infinite. And then he is able to show, right, his theorem is you're able to get this probability and utility where the probability is unique and the utility is unique up to positive affine transformation. So unique, that means unique up to choices.
So it's the same uniqueness you would get in Vienna, if you're familiar with Vienna.
So it's kind of nice, right? David Krebs, famous in his choice textbook, called this the crowning glory of modern decision theory. So maybe to highlight some of the limitations or some of the reasons philosophers can be dissatisfied with Savage, we can think about them in terms of the state neutrality axiom. There's different axioms we could think about the limitations in terms of, but maybe it's helpful to think about it in terms of state neutrality, which I have listed as this P3. Right? So this is going to assume, right, so the way, right, here, initially Savage treats preferences as a binary relation on X. We have preferences over X, but we can, he says, derivatively infer what your preferences are over consequences by just identifying consequences with the constant X that lead to them. Right? So, X is Y, these are consequences, right? We'll say that X is preferred to Y, just in case F is preferred to G, right? Where F is the constant act, right, that maps every state to X, and Y is the constant act that maps every state to, or excuse me, G is the constant act that maps every state to Y. That's it. Okay. So then we have not just a preference relation on acts, we have a preference relation on the outcomes. And what this P3, this state neutrality claim is saying is that if you prefer, this is P3, if you prefer X to Y as an outcome, then if you consider the act F, right, that delivers, let's see, it's just some arbitrary act F, but here the notation means F with the X as a superscript and E as a subscript. This means, I use this notation to mean that it's the act that's going to give you exactly whatever the act F gives you outside of E. But within the event E, E is here a subset of states, a particular event or proposition. Within E, it gives you X. It gives you the outcome X. So you can take any act you want and put this little notation next to it. It means just take that act, except vary it on E to match it to the corresponding constant. Okay? So this says that should be preferred to if we varied the same act in the same way, but put Y in there instead of X. Okay? Does that make sense? Claim? All right. So here we can see this sort of axiom is really requiring Savage to assume a kind of independence.
I'm confused by the fact that P3 says, for all F, X is referred to Y if and only if F is referred to X, rather than X is referred to Y if and only if for all F than. Is
That's right.
the distinction
Yeah. I think it does have that difference. So the definition of what it is for X to be referred to Y, that's just in terms of the constant X. So we just find the constant act X, and we find the constant act for Y, and we ask if they're referred. And that's what we're meaning by X being referred to Y, right? And this is a different claim. This is a claim about preferences over lots of acts that are not constant, or far from constant. but our preferences are somehow constrained by the fact that we have a certain preference with respect to constant acts. So if I prefer the constant act that always gives x to the constant act that always gives y, then this further thing has to hold. If I take any old act and any non-null event e, non-null part doesn't matter so much, then if I vary e to make it x, to make it the better outcome intuitively, that gives me a better act than if I vary it to make e, to make all the states in e give us y, the lesser outcome.
But
Does that make sense?
I think Matt was referring to like the order of where the universal quantifier is, like outside of the infinity or inside the infinity, and you're claiming this does make a difference?
Can you repeat the question for the recording?
So the question is, where is the quantifier in this P3?
Or does it matter? Like when I read it, like it felt to me like it was in the wrong place, but now I look at it, I'm like, maybe it doesn't make a difference where it is.
Oh, yeah, I mean, so I think it is in the right place. I think it is where I mean to have it, right? I mean to be claiming that you take any act, right, F, if you vary it on event E by giving it a better outcome rather than a worse outcome, you should end up with an act that's a better act.
Yeah, but I think it doesn't matter because like x greater than y doesn't depend on f.
Yeah.
So, okay, then it doesn't matter.
You can just change it up. Yeah.
Okay,
Okay, thanks.
cool. That work? That clarified?
I think I would, yeah.
Okay. All right, good. So this axiom then is kind of requiring a sort of like a state neutrality here, but a kind of independence between states and consequences. So you can sort of see that in a simple example. Here's an example that's sometimes given to this. So let's say we have two states or events we're interested in. It's either going to rain or it's not going to rain. Let's say there's two acts, F and G. And F is the act, let's say we're dealing with a very coarse-grained understanding of consequences here. So my consequences, let's say, are just I have an umbrella or I have a swimsuit. Right? And let's say F maps both of these to U, right? G maps both of these to S. Right? Now let's say, right, that I really think it'd be really bad to have a swimsuit instead of an umbrella if it's going to rain. So I think this cell on the table is really bad, right? That might motivate me to say I prefer F to G, right? So Savage is then going to interpret that as meaning I prefer umbrella to swimsuit, right? So P3 is then saying, right, since this is the better outcome, U is the better outcome to S, I could vary this, let's see, and if I, let's see.
Right, but this is only because they're constant, right?
These, yes, so the preference between the axes is they're constant. Yeah. So let's see, so if U is the better one, so if I replace any S with a U, I should get an act that's better than G, right? Right, is that right? Or yeah, and if I replace S with anything here, I should get an act that's worse, right? So if I put S in for not R, if I do U not S, so the act, I call it F prime, it gives me an umbrella when it rains, and it gives me a swimsuit when it doesn't rain, right? This is going to say that would have to be a worse act than F, right? Does this make sense? It's kind of a dominance.
If R not R, R non-null.
Yeah, exactly, right. Given R not R. But of course, this is like not necessarily plausible, because that would actually be the preference you'd have, right? And sort of reasoning or motivation you give, or someone like Savage gives, is a misapplication of the theory, because the outcomes are too coarsely grained here, right? We need to factor in things like, well, getting an umbrella when it rains is a different outcome than having an umbrella when it doesn't rain. Having a swimsuit when it rains is a different outcome than having a swimsuit when it doesn't rain, right? So if we want to make P3 plausible, if we want to make state neutrality plausible, we're going to have these really finely grained outcomes. Right? Problem with that, right, or at least one sort of problem with that, is that then, right, that's going to push against some of the other requirements of Savage's theory, in particular the assumption that we're forming preferences, or the agent's forming preferences over all different possible functions from states to outcomes. Right? You might think intuitively there, like, it seems like for us to be able to meaningfully interpret those kinds of preferences, it should be that all the acts are like, logically sensible. That is, that they're not mapping states to consequences that are incompatible with the states. Right? If I try to do the sort of naive thing here, and I put in, I say, okay, the outcomes here, they're too coarsely grained, so I'll individuate them a little bit by putting information about whether it rains or not into the consequence. So maybe I say, my consequences should actually be like umbrella and it's raining, and umbrella and it's not raining, and so on. Right? Now Savage is going to require I have to be able to consider, for example, the constant act that in all the different states yields this same, or yields one of these consequences, say umbrella and rain. Right? But then that's kind of difficult to interpret, like the act that when it's not raining yields the outcome that I get an umbrella and it is raining. Right? So this is a kind of this is sometimes called in some literature the rectangular field assumption, that we can form preferences over all these different kinds of functions. Right? Okay, so we have the state neutrality assumption is kind of pushing in the direction of having really finely individuated outcomes, but the rectangular field assumption is kind of pushing in the direction of not having such finely individuated outcomes. So there's one kind of problem. All right, different sort of problem is one Daniel will probably talk about more in the Jeffrey framework with the dualism. Right, so here we've noted probabilities are only defined over states. Utilities are only defined over consequences. Right? Acts only get expected utilities. They get expected values. In particular, they don't have probabilities. Right? So this model doesn't in any way have a sense of an agent having degrees of belief about her own behavior, her own actions. Right? So I think that's a limitation of the model. In a richer framework, we want to be able to model the agent having beliefs about her own actions. Another sort of issue that's probably like the most popular critique of the Savage framework within philosophy is this act-state independence issue. So this can be illustrated with another. Yes?
I look at this and I'm a little like, my naive reaction to the rectangular field assumption problem is that it's kind of just a mistake, and you should be able to just like rewrite it with the type of consequence to be like for each state there's a different class of consequences, and you'd be able to get like the same axioms and the same result. Is that true or false?
So is your thought we could get rid of the rectangular field assumption, or not still do like the same thing without that assumption, or is your thought no, like that assumption is okay as long as we just individuate our consequences, right? And we'll always be able to go back.
Like I'm imagining like I have a set of states, and I have a set of like. Okay, no, never mind. I noticed my question's confused.
You want a dependent type.
Yeah, I want a dependent type thing, and I feel like I expect it to work out.
Yeah.
Like I will expect. Like my question is, if I try to do the dependent type thing, will it work out or will it not work out?
Could you repeat that question?
Yeah. So the question is, can we do a dependent type thing where you have basically different consequences that correspond to different states?
Right.
Yeah. So not in Savage, right? Savage, his measurement procedure and everything involves you have to have these constant acts, which means every constant is always compatible with every state. Now there are people coming after Savage who try to do frameworks where you can have state-dependent utilities. Right? Usually it's tough to get the same kind of measurement result. But there is a whole tradition in economics trying to do stuff kind of like that. Good. Okay, but regardless of whether we can solve that problem, so maybe you think, oh, maybe we can build a theory in the Savage framework that gets around this problem of state consequence independence. There's still a problem of act-state independence, and this I can illustrate with another example. Do we have it right here? So this one is a classic example that Jeffrey talks about, and other people. So this is like the decision problem where you got to either decide whether to smoke or not smoke. And your two possibilities are you might not get cancer, you might be healthy, or you might get lung cancer. Right? And then let's think how you'd order the different outcomes. So suppose in the example, oh, you kind of like smoking a little bit. So the best outcome would be you get to smoke and you don't have cancer. So I'm just using these numbers just to represent the ordering of the outcomes. Right? So that'd be like the best outcome. Second best would be that you don't smoke, but you also get to stay healthy. And then worst outcome is that you don't smoke and you also get cancer. Okay, so here, right, a consequence of P3, a consequence of the state neutrality assumption is maybe we're going to be able to argue that in Savage's framework, you should prefer smoking to not smoking here, right? Kind of dominance argument, right? If we compared, like, say, 4 and 1 to 3 and 1, right? P3 is going to tell us that 4 and 1 is better than 3 and 1. If we replace the 1 with a 2, 4 and 2 is better than 4 and 1. So by ordering, 4 and 2 is going to be better than 3 and 1. So it's a statewise dominance principle.
Did you choose the notation so that smoking is a state and cancer is a consequence?
Oh, I'm sorry. Yeah. I didn't have it as S. Let's call it something else. Let's say, I don't know, P and I will let P up there. I'll say Q and not Q. I don't know. Is that okay?
Okay.
Yeah. They should. I mean, really, they're functions. So I'm writing this in the kind of more Jeffrey notation. We call them Q and Q prime, and they're really functions from the system. And then I have C here as the consequences, which is also perverse, but I don't know. I could call it X, not X. Yeah. My apologies. Okay, but it makes sense that P3, right, is going to tell you got to prefer Q to Q prime here. Right? It's going to be forced. But of course, this is fallacious reasoning, to use this kind of reasoning, to think that you should prefer Q to not Q. And the sort of response Savage would have again, you've misapplied in the theory. You need to specify the states in a way that they're independent of the act. So here the problem is, right, Q prime might actually be a better act than Q because maybe Q prime is going to influence us to be in the overall better state, the state where I don't have cancer. So there I'll probably get 3. Whereas if I do Q, that's going to influence us to be in the state where I'll get cancer, the worst outcome, right? So Savage is saying there's got to be a kind of independence between the acts and the states in order for the theory to apply well. One sort of word that's okay. That's just another constraint you have on how you have to formulate the problem. Now you have to be careful to formulate the problem in a way where your states are independent of your acts. Another issue is there's an ambiguity there, and like in what sense do the acts need to be independent of the states? And this is what leads to the evidential causal decision theory debate.
Probabilistically dependent? Where's my probabilities over actions?
Yeah, exactly, right? So even stating those kinds of problems is difficult. But whatever kind of independence is supposed to be, whether it's probabilistic independence or causal independence, right? It's some assumption about your beliefs, right? And Savage had wanted to infer all the stuff about our beliefs just from our preferences over acts. It was supposed to come from that. But here he's having to make an assumption about what our beliefs are in order for us to frame the problem in a way where he can then go photograph what our beliefs are. Right? So he's kind of not really getting totally beliefs out of preferences. Okay. All right. I think I'll conclude there.
I'll give you a taste of the Jeffrey-Bolker framework. We'll get it on the board, then we'll do our 5-minute break. All right, so to redraw the picture that Gerard out there in symbols, I'll draw it here in a picture, and then I'll draw the Jeffrey-Bolker picture. So in Savage, you have your kind of state space, and then you have an algebra over it. Then you have some kind of set of consequences over here that are going to be ordered in some sense, and some stuff could be comparable. And then you have, so this would be C, and then you have your acts A, which are all these, functions from states to consequences. So you have this kind of tripartite system. Jeffrey-Bolker says, no. Everything's the same type. You're in the world like anything else. And so in Jeffrey-Bolker, you kind of smush them all together into just one big, if you want to think of it as state space, it's one big algebra. Where the algebra, you could think of these as possible worlds. We'll see in a second that's maybe not quite the right way to think about it, but to make it a little continuous with Savage. And then you have an algebra over this, right? So you have a big Boolean algebra that has some conditions on it. And the agent, importantly, has ultimately something like probabilities and utilities defined directly on every proposition in the algebra. So you don't have this three-part system. So the agent, if there's acts in here, right? So if this is an act partition, for example, the agent can assign probabilities to whoever acts. So there's already a sense in which it's kind of more embedded. So we'll get a little more careful and precise about the algebra, and then I think we'll go for the break. Okay, so I'm on section 3 now. Yeah?
So, what should I think of as the points of this square? Like, are they lists, say, of, states, consequences, actions? Or should I keep this partition picture in mind? Like,
On this side you're asking?
no, actually, like inside. Like
Inside.
What are the points of that?
If you want to think in terms of points,
Please repeat the question.
how do I think of points in the picture on this side? You'd think of it the exact same as you would think about it here, except a little enriched. So over here, these were kind of like features of the world that you don't influence. Over here, these are just all the features. A single point would specify every feature of the world. Any question you can formulate about it, that point would give you an answer to it.
Is it like a world or like a world trajectory or?
World here, we mean everything. Is it a world or a world trajectory? World here, we mean, I think world trajectory would be your thing, but we call them worlds. Here, a world is specified every possible fact the agent can consider.
Including indexable?
Any possible fact the agent can consider. If she's considering indexicals, there's indexicals in there.
So a single point in this space is a world with every fact about that world.
Yes, and you'll see technically we don't have points in the space, but you can approximate arbitrarily close to any point you'd want in the underlying space using ultra filters. Probably talk about that more in the kind of Q&A, so it's not totally inappropriate to think of points in this space, but it does break down some kind of distinction. Yes?
There aren't points, there are just very tiny regions that you haven't zoomed in far enough on.
Yeah. Question.
How do you reconcile what you just said with the introduction earlier where you said that you stop making the distinction between sets S and C? So you're now going to have one set where...
Yeah, there is one set here.
Repeat the question.
How do you distinguish between S and C in this framework? S and C, it's just all the same type. And because you don't even think of actions as a function that takes you from a state to a consequence. An action would just be this. So if the agent does this proposition becomes true, this little edge becomes the new space, and now that's the new world, and there's no functional behavior.
Oh, but I could still think of it as like an endo map going back to itself, right?
I just think of it as following off.
But
maybe there's a way in which you
and
say
then you say, right, I can look at this map that goes from itself and look at the image of it as the actions are done or something, and then I think of the partition induced by this. If I go directly from that picture to here, is that rough to believe?
I'd say I don't actually understand exactly the proposal you have.
what? I'm trying to understand where the partition comes from.
Where the act partition comes from? You're trying to understand where the act partition comes from. Is that true? Or what do you mean the partition?
You were talking about the act, the partition you've just drawn and the parts of the space.
So maybe I'll talk about the algebra for a
Okay,
second.
yeah.
So you look in your handy dandy handout, definition 1. So I can't draw this fancy A very well, but I'll do my best. We have this kind of, I don't know. Yeah.
Wait,
kinda-
that's an A?
Yeah.
Look at you!
That's you.
It's an A. So you have your algebra, and right. So Boolean algebra closed under. If you're thinking in terms of an algebraic set of sets, it's closed under union, intersection, complement. If it's a sigma algebra, it's closed under countable versions of these operations. But in general, we're not going to assume it's an algebra of sets. In general, it won't be an algebra of sets. So we haven't said things like meet and join. So you can do logic in this space. And the particular algebra that Jeffrey-Bolker works with has two important properties. It's atomless, so this is this condition down here. So it's atomless if for every member, every proposition, A in the algebra, I'm not going to write in the algebra, there's some other proposition let's say B, such that B implies A, and B is not the empty, it's not the bottom element, and that's implied in how I set up the definition. Because I'll call A prime the algebra without the bottom element. So this would say that take any member of the algebra, like this one, I can always cut it up further into at least 2 subcomponents, and I can do that infinitely far. So there's no atoms. So for the people who are familiar with measure theory, you wouldn't have any singletons of points. You wouldn't actually have a statement describing the full world in the space itself. The algebra is also complete in the sense written down here in that it has suprema and infima defined on it. Kind of technical condition. If that doesn't mean anything to you, don't worry about it. But what we see is the kind of core innovation is instead of having this really 3-part system where you have very careful typing, but then you can run into these kind of logical issues, you just have everything in the same space with the same attitudes, or different attitudes defined all in the same set of objects. So this is one reason why we think it's interesting maybe for thinking about things like alignment and embedded agency, is you can reason about yourself in this space much easier because you can think about acts here than you can in Savage. When we continue the talk, we'll start looking at a few of the different ways this behaves, and then a few kind of other upshots of the framework. So I think we'll do our mandatory 5-minute break now. Okay, I'm going to set up my clock, and then I think we'll start again. Alex, I have half an hour now? Do we have half an hour? All right, so we're back in this Jeffrey-Bolker picture over here. Just to be clear, I defined A prime as A minus the bottom. I'll just remove the bottom element, just to be clear for notation. It says so in your packet. Okay. So review, right? We have this complete atomless Boolean algebra. So this will allow us to do a cool thing, which is to keep the probability on every member of the algebra other than the bottom element strictly positive. I can talk about that a little later, but just flagging that before, right? A lot of the conditions Gerard had to state for Savage included things like, if E is not null, then this holds. We just ignore the null. Like, there's no null sense in this theory other than the bottom element is the only one. If you're in an algebra of sets, that's just the empty set. So when I say bottom element, it's the thing that is definitely false. Okay. The game is very similar to here, to use Gerard's language. Right here we had a ranking over all the acts, preference ranking. You write down some axioms, and then you prove a theorem that says if this ranking satisfies those axioms, then you can represent it as this expected utility maximizing kind of preference relation. And in general, it often goes both ways. Also, if it satisfies it, then if it's an EU representation, it'll satisfy the axioms. We're going to try to do the same, or you try to do the same thing in Jeffrey-Bolker. Except here the preference relation is not over this particular kind of object, it's over A prime. So you don't include the bottom element. I don't ever ask you how much you prefer the empty set to something. Any 2 propositions in the algebra, I say, hey, how do you feel about this one versus this one? And you tell me which one you prefer. And then we have these axioms. I'll call our attention to 2 or so. And then you prove a representation theorem. Okay, so just like the Savage, we have some kind of basic ordering axiom. It's axiom 1 and 3. So if we look at axiom 4, this is, I think, one of the core ones in Jeffrey-Bolker. I claim it's super intuitive, but it's also weaker than stuff you might have seen elsewhere. So let's take a look at it. So this one says, if you have 2 members of your algebra, I'll draw here, let's say A and B. Okay. And they're disjoint, such that their conjunction is equal to the bottom element, so they're incompatible. In this picture, that's because they're non-overlapping. And you prefer A to B, then it has to be the case that you prefer A or B to B, and you prefer A to A over B. So it's kind of called averaging, kind of taking a weighted sum of the two is a kind of intuition that should lie somewhere in the middle. It's also sometimes called or vel or v in betweenness because it's saying that this is in between these two. It's kind of intuitive because if you think of it in terms of a gamble, right? So say you prefer $20 to $10, you say yes. Well, how do you feel about some probability of winning $20 plus some probability of winning $10? Well, then it should be that lies in between. So that's one of these kind of core things, and you can also see that it comes down with you can put everything as well with indifference. If you're indifferent between the two, this also has to be satisfied. So this is like super intuitive, I think. It's just saying when you mix between these two things, it lies in between. Okay. I'm going to turn and tell you a little bit about how we think about expected value here, and then I'll come back to this and I'll give you a short little puzzle. Okay. So, in Jeffrey-Bolker, what you end up with, like I said, is, we'll talk about uniqueness in a little bit, but for now think of it as a probability function P, utility function U, and it's all defined in the same object. Now, when you look at the utility of A, for example, and you cut it up in any way you want, and let's call this, A1, A2, A3, some subpartition of A, then you can write down the full utility of A, so how good A would be, as the utility of A1 times the probability of A1 given A, plus the utility of A2 times the probability of A2 given A, plus the utility of A3 times the probability of A3 given A. Look right to you? Mm-hmm. All right. So I take a proposition, cut it up any way I want, and I can get the value back in this. And this is why we say it's expected utility, right? You can break it down, and then you write the utility of something that in Savage would have been something like consequences, but here there's no distinction. Any way you want to carve up the world, then you can get back the expected utility kind of representation. So with that understanding, I'll come and give you a little puzzle, and I'll ask you at the end of it to turn to the person next to you for 2 to 3 minutes and think it through. So this looks a little like independence, if you're familiar with independence in von Neumann, which says if you have some kind of consequence, or more generally some kind of gamble, and you mix it, and you prefer it to another gamble, and you take them both, and you mix them with a third gamble in the kind of same way, that the mixture will kind of preserve the initial preference order. Okay? I'm going to write something similar down here, and I want you to turn to the person next to you and figure out whether you think this holds true, given what I've said here. And if it does, try to think, can you show it? And if it doesn't, can you think of a counterexample? So the case would be something like we have some proposition here, C, and it would be that we prefer A to B. They're all disjoint in the background, so A and B is equal to the empty set, and then same with C and so on. Is it the case that if you prefer A to B, then for any C, you'll prefer A or C to B or C, right? So assuming they're all disjoint. So if you prefer A to B, do you prefer A or C to B or C? Take 2 to 3 minutes for the person next. Yeah, you question?
What are we allowed to use? Like what assumptions? Just that one, or?
You can look at the sheet as much as you want as well. But I think it's most informative to look at this one, and also maybe this, just to remind yourself of some kind of submission. But I think this is the place to think it through. Yeah, so I want to hear discussion. The mic should pick it up.
problem with 90. I think it's I remember you giving up the numbers. I think
So, I think one question maybe is designing implementation of something that's already been stated.
Yeah.
Oh, okay, so I was
C is another one that we would need, and C is like B.
What do you see?
Yeah, maybe you could clear a prep for that. A or C. Yeah, that
The C is much more likely than A, E is much.
All right, it's kind of, I know people are still talking, but I kind of want to get to some other stuff a little bit. So let's bring it all back together. So I know I've already given this to some people in the past, and then we had a discussion. So to someone who I haven't had this discussion with before, and who didn't already come in knowing, wants to take a shot. No worries if not, I can just explain it to you, but I'll give. Yeah.
I think the answer is no, because if I prefer C to A and B, so it's both A and B, but the probability of C given B or C is much higher than the probability of C given A or C, then I might choose the B or C option.
Exactly. That's exactly right. So I'll draw another picture to make this evocative. Okay, so imagine that the utility A stayed the same, but the probability of A was really small. Okay. Now, your example was suppose C is great. Suppose C is like you win a lot of money, and the difference between how much you care about A, or do you still prefer A to B? But intuitively, it's much smaller. This is like the difference of like some small sum of money, whereas C is so preferred to both A or B. Then you'd really prefer this gamble, I think I did the other one, because I usually do the example.
Yeah, A or C.
Yeah.
Yeah, my example,
So,
yes.
yeah, it needs to be B, needs to be small. I usually do it where like C is you get tortured for a long time. You have the you in mind. So in this case, if you mix B and C, because the events carry with them their own probability, and this is a core feature of one core feature of the Jeffrey framework. The probability is different from the agent's own point of view. You don't get it from arbitrary mixing over states, or in DNN you don't have these arbitrary gambles. all the gambles are kind of internal from the agent's own point of view, you would prefer taking these two, or one of, the union of them, or the or. Because, like you said, this gives you a higher probability conditional on B or C to get the really good outcome. Right, whereas if you take this, then even though this is better than this, kind of the gamble has a much higher proportion of A worlds in it, and that's just not worth the trade-off in reducing the probability of getting a C world. So I think this is like a nice evocative case of where I think some version of embedded or naturalized, or from the agent's own point of view, being closed just under logic and not under arbitrary functional combinations that kind of build a VNM style structure in the framework, actually get you something different. So that's a kind of intuition for averaging, but how this doesn't actually get you something like independence in the strong sense of VNM. Because you kind of can't state it, right? Independence requires that you mix with the same probability between the two gambles, and that's just the thing you can't do in general here. Okay. There are these other conditions. I give an example of impartiality in footnote 6. I'm not going to go through it, but if you care. It's there. I think it's the most awkward of the axioms. In general, you want to get an expected utility representation out. You have to put that structure in, just like with any theorem, and that's the one that just screams out, this is an expected utility representation. I'm going to push past that and go to the uniqueness result. So I'll state it, and then Gerard will discuss it and think about kind of how to deal with it. So I'm going to write this one out, both to write it out so it's up here, but also to give you time to think about it if you're looking at it. Okay, so we're just going to say, let our preference racking satisfy the axioms. Then there exists I'm doing the Bolker existence. I'm going to change this. I was writing the wrong thing. So what you do get is you get this existence theorem that says that if you have the preference ranking on the algebra, I can extract some probability utility K. That gets you it. Just like in Savin. But the it's a little weaker. So this is the uniqueness theorem. So if we have two different probability measures on, I gotta draw the fancy A. Oh, is this something like this? On this, and we have two signed measures. So if you look in the theorem above, there's kind of three objects. There's a probability, there's a utility, and there's a signed measure, and they all combine in the way it says. You can think of signed measure as another way of writing down value, but the big U is the kind of decision relevant one. So if you have this, and you have these little two signed measures, V and V prime, also on the same cursed object, then P prime, V prime represents the same preference ranking. I'm going to say this as PV, if and only if they're related via the following transformations. V prime, so the new one, is equal to the old one times some constant A, plus B times the probability, the old probability. And you have P prime is equal to some other constant C times the old value kind of function, plus dP. So this looks kind of dark because you have value and probability somehow entangled in this representation. Whereas in Savage, they weren't, right? There was one unique probability function, and then you had a class of utility functions that varied in just a positive affine transformation kind of way. And there's a few conditions on this. So one of them is that AD minus BC has to be greater than 0. What this is going to say is that the transformation is increasing. This is that it preserves the order of the preference rank. So if you then write out the U in terms of these, which are near the top of the next page, that means that whether you're working with U or U prime, the preference ranking will stay the same, which is really important for representing the same preference ranking. It also has to be the case that C times the value of the tautology, the top element, plus a D equals 1. This is just to ensure that the probability of the top element, P prime, equals 1. Right? Because if you look here, the probability of T is going to be 1. So that just reduces to C VT plus D, which is this, and that has to equal 1. So that's just normalizing things. So you get a probability. And then you also need it to be the case that negative D over C is not equal to VA over PA for any proposition. For any proposition A in the algebra. And if you look on the next page, again where I write the transformation, this is basically a don't divide by 0 kind of condition. Because if you had this, then you'd end up dividing by 0 at some point in your transformation. So they all have a kind of intuitive thing, but you're still left with this, for some, uncomfortable entangling of value and probability. So if this looks totally ugly for you and you didn't follow, that's okay. That's part of just working through Jeffrey-Bolker. You stare at this for a bit, you don't really know what's going on. It's a fractional linear transformation. Gerard will talk about ways to deal with this if you want to have a stronger uniqueness result. So if you want to have a unique probability function and utility function unique in the same way that Savage's or VNM's is unique. There are ways to get it, and Gerard will talk about that now. Question? Yeah.
So just making sure it's something like if somebody is doing a bunch of planning for a possibility, there are sort of two ways to interpret it. One is that they think that possibility is likely. The other one is that they care unusually much about what happens if that possibility occurs.
I think that's right, yeah. And Abram has a nice post about this Jeffrey-Bolker rotation, which is kind of going into the intuition behind this, and that's part of it. Is you can kind of trade off between how likely you think something is and how much you care about it, and this particular transformation will preserve all the kind of preference-relevant structure in pretty much the way you described.
Mm-hmm.
Is there an intuitive reason why that doesn't happen in Savage? Because when I hear that, it feels like, well, yeah. Why
Yeah.
don't we get something like
Yeah, do you want to talk about, because you basically build VNM in Savage, and that's why you end up with.
Yeah, so you get your probabilities first. So first you try to figure out a comparative probability measure, and then you have results that basically you get a ranking of all the different propositions, all the different events you can form from states, and you get a unique probability measure on that. And then you can kind of associate acts as lotteries, because now every act corresponds to a probability distribution over outcomes, and then it becomes kind of like VNM. Right? The axioms will get you stuff like independence, that's the whole thing.
And the core is that the functions here are just much richer, right? You have every possible functions from states to consequences. So if you think of whatever the underlying distribution is, you can just vary in like a kind of probe it with arbitrary functions. You pick two consequences, and you can start to find these kind of in-between points. And you just can't do that in Jeffrey-Bolker, because the algebra is, in a sense, much smaller in that it's not closing these arbitrary ways of gluing together things, of gluing together, states and consequences. It all comes from the agent's theory of the world, how likely she thinks things are.
Maybe I should have talked about like that in terms of the way that you can find out in Savage whether one
Might be useful.
proposition is more likely than another. So we take two, we'll say non-null events, E and F. They're subsets of our set of states, right? Let's say that we have two consequences, X and Y, X, Y, Z, Z, these are consequences, and we'll assume X is preferred to Y. So if I consider an act that looks like f of s, it gets you, let's say it gets you X, the better outcome on E, it's either disjoint events, E and F, disjoint. We want to know which one's more probable, so it gives you X on E, it gives you Y on F, and it gives you Z otherwise. And then you take an act like G of S that just rotates where you get the better outcome. So Y on E, X on F, and Z otherwise. And Savage's sure thing principle, which was P2, is going to get that it doesn't. Is going to return the verdict that it doesn't really matter what Z is here.
It's not,
Oh, yeah.
You can finish. It's on different point.
A different one. Okay. So here, right, we're going to read off your preference between G and S, right? Which one do you think is more likely, E or F, right? So since you want X, right, if you prefer F to G here, then we're going to view that you think E is more likely to be the true event than F, right? And we can do that for any disjoint events, and we get sort of ordering on disjoint events, and we can use logic to figure out the ordering on all the events from that. And then you get your probabilities that way. Okay.
Yeah, completely different question. I think what I'm most curious about is because what we lost with Gerard and Savage with Jeffrey-Bolker is the crisp notion of action. How do you get actions in Jeffrey-Bolker?
So in
Repeat
Jeffrey-Bolker,
the question.
oh yeah, in Savage we had a kind of clean place where the agent sat, clean sense of action. It's the setting. In Jeffrey-Bolker, you just have this. This represents the algebra. I mean, this is really like the state space, but you have then a whole bunch of partitions across it and propositions. Normally, when people model a decision problem, they just take some kind of partition, and they say, this is a decision problem, where this would be like your first act, this would be your second available, and your third. You might say, well, where do these come from? And I think the first thing to say is,
right person to ask that question.
well, one thing to say is this is already also made, you're also doing this pretty theoretically in Savage, right? When you set up the problem initially, you're not deriving this from how the agent thinks about, you're just coming in and setting it up. Or the agent already has to have some way to think about, set up her own Savage space. But Savage doesn't tell you anywhere how you get the right states, consequences, and functions. And so I think in both cases, it's just not a question people have explored that much about where the acts come from. Now, in this case, I have a whole count that I've developed, but I don't want to hijack the session, but I'd be happy to talk about it at
It
some
just
point.
looks like you would get evidential decision theory. Get naive.
So evidential decision theory is, if this is your decision problem, evidential decision theory says, do the act you prefer.
Right.
And we'll talk at the end, if we have time,
We have time about how you do causal decision.
Right, this is the decision framework, as in it expresses the attitudes the agent has, but you can build causal decision theory in this framework. You can build evidential decision theory in it even more straightforwardly, and that actually allows you to compare them, whereas in other frameworks you can't make this distinction. And that's partially because this already involves setting up the independence in a very special way, whereas in this you don't need to, right? There's no requirement of any kind of independence here. That the independence judgments come in at the level of making your decisions, not setting up the problem. And so it kind of allows you to put things on the same foot.
Can I say? So the reason why we can disentangle probability and utility in Savage but not in Jeffrey is because in Savage we assume a preference ordering over I can't even remember acts.
Yeah, a lot of very structured acts.
Whereas the thing we assume a preference order over in Jeffrey is already a mix of probability and outcomes.
I would say it's like a much less structured space. You don't have these arbitrary ways of gluing together different things.
Results.
Yeah, states and results. It all has to supervene on just the logical structure of the space as opposed to the functional structure here.
I have a slightly different way of answering it.
Yeah.
So in Savage, there's the objects of belief and the objects of preference. And so in order to get some kind of way of mixing them together, you would have to somehow mix together those two algebras, which is, there's no obvious way of doing. But in Jeffrey-Bolker, the objects of belief and the objects of preference are the same thing. So then it's very natural to say, what if we shift around the beliefs and correspondingly try to shift around the preferences in a way that compensates?
It's kind of like Alex was saying. But yeah, but there is a way, there are things you can do, or you could think of it as either things you could do or conditions that might hold that let you pin it down more in Jeffrey-Bolker.
Yeah.
We'll turn to
Sort
Gerard.
of. Yeah, so this is sort of one thing that at least a lot of philosophers think it is an advantage of Savage that he gets a nicer uniqueness result. We'd like to be able to infer determinately what an agent's beliefs and values are, and you can't do that in the standard Jeffrey. So there's a few approaches that people have proposed where within the Jeffrey-Bolker framework you can still get unique probability representation and a utility function that's unique in the same sense that Savage did. So I'm going to write it, I think, in a slightly different way than Daniel has, because Daniel is more sophisticated than I, and he learned this stuff from reading Ethan Bolker and Peter Fishburne and such people, and I read Jeffrey, so I know it in a little simpler, or different form, without all the signed measures.
They'll be equivalent.
So the game is, right, we have your preference sorting over all these different propositions in this algebra, and I come up with some Jeffrey-Bolker representation, right, PU, where here P is a probability measure and U is a desirability or utility function. And I know if I take another P prime, U prime, it's also going to be equally as good a representation if the following conditions hold, right? They're related in this way. I take some numbers, A, B, C, D, where right, A times D minus B times C is positive. And then you have all these relationships between them. So, right, the latter utility function U prime is a quotient of two different positive affine transformations of U, one using A and B, and the other using D, C and D. So A times U plus B over C times U plus D.
Gerard, I try to conclude in 1 minute.
Oh, 1 minute. Oh, man. Maybe should I just like skip the whole thing and I'll
I'll
just
give
the
two
upshot.
strategies.
I'll just give you
two possibilities.
the upshot. One way, if your utilities are unbounded, right? So if U ends up being unbounded, then actually this all collapses. The C ends up having to be 0, the D ends up having to be 1, and you end up getting back the exact uniqueness result.
It's because of this. You're ruling out possible values of D or C, as this or equivalently U can take on more values.
So that's requiring you to be unbounded. The other proposal you can go, that's probably the more like popular philosophy or like, is to would sort of go against the economics strain of thought, is to say we can't totally determine beliefs from preferences. We need an additional primitive in our model that corresponds to something epistemic or to beliefs. So you have one way people do this is you'll introduce a primitive equal confidence relation, where like agents make judgments about which propositions they're equally confident of, and then you require that your probability measure has to agree with that equiconfidence relation. So it assigns two propositions the same number, just in case you judge them to be equiprobable, or if you judge them to be equiprobable, then it assigns the same number. That's a better way to say it. And then you can again get these numbers are going to have to collapse, and you'll get a unique result. So those are the main ways. There's also ways to do it in terms of conditionals, but those
Gerard has a nice little proof of the equal confidence one. We can talk about that in our session, which immediately follows. We can also talk about connection to measure algebras, which I think is something that's pretty fun.
and decision theory.
And also, if you want to actually understand CDT, EDT, kind of on the same footing, in the same space, we can walk you through that as well. Thanks so much for your time and attention.